Welcome, everybody. It's my absolute pleasure to welcome Gabor Fichtinger at this session of our Distinguished Lectureship Series in AI and Healthcare. Gabor is a professor at Queen's University, and he received his PhD in computer science from a different technical university, the one in Budapest in Hungary. And he is now a professor in Canada, research chair in computer integrated surgery at Queen's University in Canada in Kingston, where he directs the PERC lab, the Percutaneous Surgery Laboratory. And he works basically in computational imaging and robotic guidance for surgery and medical interventions, focusing on the diagnosis and therapy of cancer and musculoskeletal conditions. And he's got over 700 publications with over 14,000 citations. He is an associate editor for all the important journals in that field, in IEEE Transactions on Biomedical Engineering, Media. He's deputy editor for IJ-CAS, served on predominantly the MICI board. This is where I think for me he's most famous for. In fact, he was the treasurer for many years, but also on the International Society of Computer Assisted Surgery, ISCAS. And he's got many, many honors, the Tier 1 Canada Research Chair, the Cancer Care Ontario Research Chair. He's fellow of IEEE, AIMB, MICI, was a Marie Curie Fellow of the EU, and distinguished speaker at different societies. But I should really highlight with Gabor, I had the absolute pleasure of co-chairing the program of MICI 2018, which has glued us together ever since. We've been joined at the hip for, I think, 3 years over that process. So I'm entirely grateful for his support and cheerleading during that time period, which was really, really great. And today, Gabor is joining our list of illustrious speakers, and he's going to talk to us about point-of-care ultrasound interventions in the era of artificial intelligence. Gabor, the floor is yours.
Thank you. That's a humbling introduction, and I will have to live up to that expectation. And it has been such a pleasure, at least, to see you guys on the internet. My only regret is that I cannot be there in person. Well, the whole meeting is not in person anyway now, but still would be good. So, you see the title up here, and if I did the title today, maybe I should tone it down a little bit to just one topic. That's how free open source software platforms can enable the development of AI methods in the particular area of ultrasound guided interventions. This is a subject that we mutually share, and it is of great interest to us, to your center, and a lot of places elsewhere. So see what we can do for this field. I don't really want to talk about at all what we did in this field, or try to peddle to you one big pinnacle of science or another, because you guys are the #1 center in the world now in this business. So it's not a lot I can teach you about that, but I'd like to show that our humble efforts in enabling other people's research, because that's what pretty much what I do as a professor, as a teacher, is paving the way for groups, the best ones in the world or the poorest ones in the world, to practice this research and science. So let's just get to it. If I can find my mouse. And now I don't have cooperation from my computer. Now I regained the image here. I'd like to acknowledge our technical staff, our engineering staff. Many of you probably know András, Tamás, Csaba, and Kai, who are leading scientists themselves, but their main contribution to what our field has been open source software architectures and tools. And this really is their day today on the screen. So all the honors and glory and everything goes to them, and of course the funding agencies that make this happen. So if I can further comb down the area of interest of the day. That's point of care ultrasound interventions. If you look at this fairly simple procedure here, that's an ultrasound guided biopsy. That's not a technically simple one. For someone who doesn't be around ultrasound itself, the simultaneous management of the tool and the interpretation of the image in the presence of tissue deformation, motion, and all sorts of problematic issues is major. And when we are talking about interventions at the bedside, then we have an epistemological challenge as well, because we have no expert radiologists present, and the surgeons and interventionists, whoever is doing this procedure, they're not entirely sure what they are doing. And no matter how well you think you did your technical job and trained your AI systems and predictors that is helping them interpret the image, there is always a level of uncertainty that lives in the surgeon, and how we bridge that one is not a trivial exercise. Nonetheless, opportunities are immense in point of care ultrasound, as it really truly can transcend all the geographical and socio-economical limits. And if you ask me back one more day, sometime later, I perhaps can talk about the train-to-trainer programs in West Africa, working on national programs in Mauritania and Senegal to establish image-guided ultrasound interventions as their next phase of healthcare, which is an absolutely exciting and invigorating possibility. So if you think about these ultrasound guided interventions, it's the arrestingly simple concept of tracking spatial navigation that you guys know all too well is very appealing. And this concept, the tracked ultrasound navigation, that has been around for maybe 20 years, maybe 30 years, maybe longer than many of you have thus far lasted on this earth. And it's really not too complicated. Get yourself a computer and ultrasound scanner, some spatial tracking device like electromagnetic sensor here. Put a couple of sensors on the tools and the patient, and ta-da! Here is this pretty appealing, very simple looking system that you see here. And it really offers itself that I want to build it, I want to implement that. And a lot of people did, countless people did, countless companies did that, and they went bankrupt with it. So that's another interesting question, why so many people started and so few finished actually the job. And if you think about, if you now for a second are a graduate student who will think that you will kind of hack out maybe this simple Mickey Mouse navigation where you have a tracked ultrasound and then you have a sponge ball or a grape in the jar and you want to hit it with a needle, you will see some mathematical complexity. Not tremendously great if you know your ways about transformations, but still it's a computational or almost a combinatorial blow up for the number of things that you can mess up. Besides, there are a whole bunch of issues for which there are no standards, how we interpret any one or all of those coordinated systems. So if you can think how many different directions can be flipped, and trust me, they do. So that's by means no simple for even the simplest thing. And then you are confronted with reality. 20 years ago, we were happy to have wall ultrasound scanner, which cost about $100,000, and then it's pretty much lasted out for a couple of years. Once you made that investment, you tried to take out at least a decade from the machine. And you probably had a Polaris scanner that was the standard of the day. And if you were a graduate student, you might as well thought that you can hook up these devices and see yourself through to graduation. The reality these days is that ultrasound has gone mobile, has gone handheld, has gone totally El Cheapo, and there has been also a proliferation in the tracking devices, in the electromagnetic as well as the optical as well. And if you look this way a little bit further, then what you really see into these systems that we have a whole bunch of physical measurement devices that from one way or another, they are streaming digital data at different frame rates to your system. Some of that data is interpreted or pre-interpreted as position. Some others are pre-interpreted for you as images. You might even get an XY grid of pixels. Some are optical images, like you see here from a camera or a scope or a gastroscope and all sorts of things. Some are non-intuitive. Nonetheless, they are perfectly legitimate streamed signals in an intervention systems in one or another. This is a thermometer. Here, a thermocouple shows up all the time in validating ablation procedures and whatnots. Optical spectroscope, if you want to do real-time tissue characterization. Now, this is a funky animal. That's a mass spectrometry device. Who would think that this is going to show up in an intervention system and stream data at you in its own funky way that chemists do things to you with no regard whatsoever to temporal requirements and whatever else. They think they do things that way. It's an oscilloscope. Scopes are showing up, or other kind of measurement devices. And of course, the funny little encoders and all sorts of things that you may interpret as tracking data. Some of these interpretations happen at the library level. Most ultrasound scanners have an SDK. Some of these cameras, like this Interis, has an SDK, but good luck to an SDK from a thermometer. That's not about to happen, or from an aspect device. So you got to do something about that, because there is an onslaught of information that is coming into your precious POCUS ultrasound system. And so if I put a hypothesis on what is it that we are really after, then it is, we want to put together, or at least we hypothesize that it is to put together a system from standard components like this gentleman has here, a whole bunch of bits and pieces. And out of that, I want to put together a system that is reasonably invariant to the actual hardware I'm putting it together, invariant to a large extent, as much as we can, to the disease and target organ. Why cannot have a biopsy system or something from the spine as well as for the breast that I would know how to put it together? It will have guaranteed technical performance. I will not be able to say a whole lot about the clinical efficacy of that, but at least I will know accuracy, precision, robustness, all sorts of things. And I want to have it like this guy has, reasonably plug and play assembly. And of course, the honey on the cake or the frosting is that I want to have it free open source. I don't want to pay $250,000 to Nucleatron or Brain Lab or any one of those blood-sucking companies to let me do what I could probably do for free. And the promise of that is that will and should enable rapid development of translation of these new technologies. So once you think about image-guided interventions, you better get for yourself a platform that handles images for you. And indeed, it has been around, for me for 25 years is coming for the existence of 3D Slicer. Next year, it will be its 25th anniversary, and 24 for me, with working in 3D Slicer. So that's the vision and the brainchild of Ron Kikinis, a friend, and the Brigham and Women's Hospital. And Slicer from the outset, as huge as it is, as you doubtless heard a lot about it, meant for medical image analysis and data visualization, but from the outset is meant to support interventions as well. So Slicer has more than 1,000 major functions and well over 100 extensions. And what I want to emphasize about it is not the functions and all the good things that it does for you, but it has been doing for a lot of other people's money. Well over $50 million went to that. 2,000 years of full-time engineering development effort, one way or another, has showed up in Slicer. And 2,000 years, guys, that's biblical times. So if you are a graduate student now who needs to implement this platform, you should have born with Jesus just about, and about 23, you will be primed to crack your field ultrasound image. So this is a major thing to take advantage of. So it's a professionally maintained platform by engineers at Harvard, Queen's, Kitware, and a couple of other places in the world. And the current version today well past the 1 million downloads, and we have a daily statistics. So this is a stable platform as there is. And as I said, it's extended to 1 million things and working with downloadable extensions. So you're not carrying a humongous baggage on your back. You just go and you cherry pick the kind of modules and functions that you would like to assemble from the App Store. Well, I'm not going to walk you through this animal that actually born out of this multi-year or multi-decade effort, but I'd like to say a few things about nonetheless. What we really got here going is that, maybe I should explain it from the bottom up. So when we have all these data streaming sensors, such as ultrasound, spatial trackers, cameras, spectrometers, surgical robots are streaming, coordinate the data. They do things, they pinch and dice and slice and drill, deliver energy to the patient, but nonetheless, they are tracking devices as well. And just about, I should say, any sensor. That's when the thermometers, the spectrometers, and all kinds of crazy oscilloscopes are coming in, streaming data, and they have to be an abstraction interface, so that you could conveniently plug and replace any of these devices, or you could have any number of the streaming devices. And all you do is a little bit of a scripting to tell the system who belongs to what, who is tracking what is the logical relationship between them. And that goes through this PLUS interface, the public library for ultrasound interface that many of you have used. And it has been used in most of the known toolkits, the CUSTUS, the MITK, 3D slicer, and I believe it has been used extensively at TU Munich as well. Itself is doing a bunch of earthly pesky stuff, calibration, synchronization, all sorts of things that happen to these devices. And through the OpenIGT link, it provides a generalized abstract interface to your major processing module, which for us the 3D slicer core, and I'm definitely not going to talk about that because that could be several years before we got through all the functions and major things that does. For us, the important extensions that technically speaking is sitting on 3D slicer is the IGT module that is doing all the work that interventionalists are interested in, virtual constraints, breach warnings, tool calibrations, all sorts of registration of the different actors, controlling the view, as well as any other set of functions if you have for virtual reality tools, for radiation therapy, kinky stuff that you can link it in. For the important discussion today is that what else SliceriGT has to support the artificial intelligence and the new deep learning data hunger, and how this platform allows you to do recordings, automated annotations, training of the AI systems, reeling in the prediction that you have, and more importantly, interpret it. Because after all, any deep learning system is giving you a heap of pixels. And what that means in the context of these interventions at the point, at that given time, when the surgeon was dicing and slicing the patient, and suddenly what this prediction is, that's no simple business. And of course, this will have to be talking, this whole module, to the known MI packages, whoever on whatever is out there, where you will have trained your AI module. And probably you will be living 90% of your life in this too. And we will be happily doing the rest of the work for you. The bottom line is, once you put this together, you really can achieve, and you kind of wire up the application on the top, which could be breast conserving surgery, could be prostate biopsy, something like that. It's typically only a couple of hundred lines of Python code that goes on the top. And the 99.99% of the code is absolute infrastructure that you don't and should worry about it. This 0.1% is where all your smarts, your intellectual achievements, your next tenure position, your papers, your science, your patents should go up in here, and not to worry about the rest of the system. So that frees you up. And it gives you a great deal of liberty and free time and free resources to do the really important things. So for the rest of the today, in the remaining minutes, I will be showing you examples how this exactly is being used, not so much by our group, because that would be rather self-serving, but a lot of other examples from around. What else we helped other groups to do, because as I said, nothing is more satisfactory me than putting out some tools that actually enables other people to do all the fun work they want to do. So once you have SliceriGT installed and up on your computer, a lot of things just falling out of it. If you have this Mickey Mouse application of having an ultrasound, a tracked ultrasound, and let's say you want to do a perispinal injection or epidural injection, and you have a preoperative model for that, then the system is it. This is nothing you can, you need to do about it. It comes out of the box with a little scripting. You actually tell the system which actors belong together, which one depends on whom, and that's it. The application is up, and then you are ready to do your interventions. The Plus toolkit has a couple of routines for your pivot calibration, spinning calibration, calibration of the ultrasound probe with 3D printed phantoms, so all the pesky stuff that can swallow you up forever. That's kind of being provided in the background. So once you have your ultrasound, once you have your tracker, you can be guaranteed about the performance of these things. Accuracy, precision, robustness, speed, the latencies, all sorts of things are characterized as well as monitored for you as the intervention is going. So that's pretty awesome. And again, if you do the breakdown of all the open source resources that went into this monstrosity, SliceriGT on the bottom, you will find that fabled Slicer itself is a tiny little 3.5% of the code. So that's what $50 million of other people has bought you. 3.5 of the total source code. The rest of them, the Python, the NumPy, the ITK, the VTK, ask Kitware how much it cost them to, and other peoples to put the VTK in here, and Qt and the other stuff. when you look at it, your new application is this little green sliver here. It's not even enough resolution to show it here on the screen. So that's what you always want to keep in mind, that save yourself from the trouble of developing the things that you don't need. And now, well, with this intervention system or platform, a lot of things can be done and was done, but interestingly or not interestingly, in the last couple of years, the platform's significance has ballooned, and its use has multiplied, simple because of the interest and need that the new rebirth of artificial intelligence has brought on. AI, or previously known, so to speak, as machine learning among the circles, has been around, right? We have been using computers for decades to understand signal data, image data. So there's nothing new about that. What new was in a couple of years ago, maybe now almost 10 years ago, deep learning started to take up. And that's a storm that is not about to go away anytime soon. And the big difference now, as opposed to other machine learning methods, is that the deep learning really got the big hype. And there is something else. It really has enormous capabilities, not necessarily technically better than some of the classic image analysis is methods, and it's yet to be seen what problems deep learning actually is able to solve better than some other classic or not as deep learning-ish approaches. But deep learning also has the ability to for extreme domain translation, domain transition. So if you are reasonably equipped with linear algebra and you can crack a common UNet and an ImageNet data set, and you can tell apart a donkey from a horse, then you're pretty much set for good work research in diagnostic radiology or something. This wasn't the case before. That's why we probably see the blow up, the exponential blow up in all these conferences in MICAI and others, because the sheer amount of work that can be done without not so much of a preparation, and good work, good quality work, good contributions are flooding out at an enormous speed. And there is a reverse traffic as well. If you made your bones in diagnostic image analysis, you are good for the credit card industry as well, and make tons and tons of money that you will never see in our field. And of course, this is nothing again new. Once you get yourself to especially deep learning or any kind of AI, this is an insatiable appetite for data. And in fact, your 80–90% of the time will be spent on preparing and curating data. And in addition, the time and the data you spend on validation, that's a lot of people tend to forget. But at the same time, the natural state of interventional data, by definition, by custom in this 30+ years, is that it's lost. It's not recorded, it's gone to nothing. Maybe somebody presses the button to have a couple of paper printouts for the charts, but most of the data is gone. Even if somebody records image data, let's say the ultrasound stream, what relation that ultrasound ever was to the rest of the body, to the anatomy, to the surgical tools? Are there timestamps on that thing? Nothing is actually trivially existing. So that's where a platform like SliceriGT or 3D slicer-based platforms coming into the foreground, because they happen to be providing all these necessary cues. And the important enabler in this whole conglomerate is the SliceriGT module that has a number of important functions that I will show you through a few examples. One is that recording, and that happens through the universal sequences module in the platform. I probably can do this, and hopefully not. What you are seeing here is not a media recording. So mind you, this is the full 3D slicer replay that you actually see here. And if your imaging, if your interventional platform also includes camera images, RGB cameras, that's also recorded. So this recording is part of the 3D slicer recording, which puts away every single button press, every single mouse motion, surgical motion, tool motion, images, everything that happens from A to Z, that remains time-stamped, saved. So you can replay any surgery, anytime, any number of times, and interpret the images and get out all your annotation data and do your validation any which way you wish. So it's a complete a stenographic record of everything. So obviously it provides you with communication to the AI packages, how you parcel and send out your training data. And most importantly, it will help you with the channeling in the prediction into the scene like this and the interpretation. So one example that I wanted to show is Verdure Medical Imaging, is a company in California that is putting out this product, somewhat different packaging of the buttons. This is the slicer version of Verdure's. So they have multi-center studies with different hardwares in different places. EM sensors. This is a, let me see, this is a micron tracker with a telemed ultrasound, and that's another portable ultrasound with OptiTracker. So hardware is all different. You just come in and you replug any which way you want, and that's the same thing that is happening. So if you are and having the luxury of having preoperative CT, then having done the registration and having done all the recording that that SliceriGT does for you, you will have automatic annotation, right? That's a pretty big luxury to have thousands and thousands and thousands of segmented automated images for your deep learning. So it's not such a big surprise that a fairly standard UNet can then do this in the interpretation time when the patient is in. You start scanning the scan, let's say in the spine from bottom, and then the skeletal structure builds up for you, and then you get measurement of the curvature and all sorts of things. And all this is made possible by functions that the platform has. Now, mind you, when your registration is not as good as it can be in a spinal registration, you still do have some registration. So you do have some labels out. Maybe your labels are not as strong labels as for a skeletal structure, but absolutely free of charge, you are still getting a lot of weak or semi-weak labels. This is an example, again, where things can happen very fast. Once we got a phone call from our friends, Alex Golby and Sandy Wells at the Brigham, that they have a study approved, they have money flowing, cash was burning their pocket, and patients were scheduled. So what do we do here? And what they wanted to have is, well, the research is brain shift prediction in neurosurgery. And what they had to have is the bread and butter data collection system that was not up in the operating rooms. It's nothing miraculous, just track 3D ultrasound with OR sterilization requirements and calibration and what, get into the OR and register that with preoperative MRI and be able to acquire intraoperative ultrasound. And then Sandy Wells comes in, the great Sandy Wells with his AI powered brain, And out came this fantastic world-class research program, and it has been cracking patient data for the past several years. And again, our kind of pride and glory in that it went to collecting data to the first human trial 3 weeks after the first phone call. This is a pretty quick breakthrough. Again, this system did not make any clinical decision. It was sitting there collecting the data without interfering with the standard of care. But that one it did in pretty record time. And another kind of bonus work that we did that through OpenIGT link, as you normally want to do that in a interventional procedure, you want to clone the FDA-approved, Health Canada-approved system to your workstation, so the standard of care would never be compromised. And we also cloned a Zeiss stereo microscope out to the slicer and back and forth. So that was also very easy to do. And once we were up in the Brigham, we could do that. Obviously, we did the same for the Medtronic Stealth Station for our friends in Austria as well. Again, Medtronic is responsible for the hundreds of tools that are being handled in the operating room. You have a cloned workstation when you do your data science. That's another one from the Brigham. Now, this is interesting. Their fabled fusion ultrasound biopsy program, again, between Claire Tempany and Sandy Wells. And this was the enabling work that helped them develop the deep infer platform that is that pretty much represents the pinnacle of science and AI techniques in this field. At the time, all they needed is a simultaneous transfer beam mode and radio frequency ultrasound, tracked totally differently optically and with an EMU. And again, look at this production. That was scheduled up. They were desperate to put these 20+ people to use. And this was another fairly quick development of the platform. Again, this has been in there for several years now. Hundreds and hundreds of patients have been through this and enabled the great AI program that Sandy Wells must have talked to you about a number of times over the last couple of weeks and months. Our friends, Kitwer with Capistrano Ultrasound, have built a small animal imaging lab. I don't want to go through the details yet, but you see what it is. Ultra high frequency ultrasound imaging the mouse for preclinical research and validation studies. Last couple of minutes, I'd like to say a few words about self-servingly what we do here at Queen's with this platform, for example. This breast conserving surgery, where our concern is the great deal of tissue loss and the very high rate of resurgery. So if you manage to conserve the breast in this it's a difficult procedure. It's doing surgery blind in a short pocket on the most mobile structure of the human body. It's much more mobile than the brain it is. And we need to achieve complete tumor resection with little cosmetic loss. And the reality is that huge number of women, depending on where the practice is, this is Memorial Sloan Kettering or TUM or somewhere in a hospital in Munich, it's probably 6%. Out northern Canada, 200 kilometers from Kingston, and that's 47%. It's appallingly high. And that's where you want to be. And in order to have some healthy margin, this is the kind of lumps that is routinely taken out. This is what 4 or 5 times bigger than the tumor it is, because surgeons apply liberal margins as they have no way of saving the tissue. So here is then good old tracked ultrasound concept. Why don't you have a needle on the needle EM track? You harpoon the tumor, you track your ultrasound scanner, you figure out where the tumor is, and then you track your electrocautery and cut out the tissue. If the tumor is not too big, as it is not too big in early stage cancer, then it's locally rigid, and this hook actually stabilizes the tissue. So it's very simple stuff, really is, once you have a platform. We rolled it out, again, record time to clinical use, and over 60 patients now. We are pretty happy that there is no compromise on the standard of care. Everything happens as it should be, except we saved almost 1/2 of the healthy tissue removed. So we now have a lot of very happy women who don't have to go through reconstructive breast procedures. So that's a huge gain as far as I am concerned. And this is kind of also interesting. All the patients that went to have resurgery had negative outcome. How can this be? Well, with navigation, the margins are so tight that the cancer was burned, incinerated. 5 millimeter, 5 millimeter tissue is incinerated when you use the hot knife. So that the laboratory sample had cancer on the margin, but the cavity itself and the patient was already free. So this patient still could be pretty pissed that they had to go for resurgery and absolutely no cancer was found in them. That is because the surgeon incinerated the remaining cancer. So what can we do about this is another interesting question. I'll come in a second. And of course, one of the challenges in that the surgeon needs to contour, or better yet, a radiologist needs to contour the tumor, what we resect, because after all, we are navigators. We can only resect what they tell us to do, and that we can do very accurately. And of course, then we unleash deep learning and all sorts of things. And just wanted to flush this one up, that when you do deep learning on an ultrasound image, then you can become pretty good. Like we think with the standard DL metrics are very good, except we are dealing with human surgeons. First, they want actionable information. A surgeon would never look at a contour like this, because this is not resectable in the breast. These contours are drawn by a crazy radiologist who has never taken out a piece of lump. So they are totally irrelevant to the surgeon. So show these metrics to a surgeon and we'll be laughing at you. This means absolutely nothing to them. Actionable information that accounts for all these variations, and then you get end up with this, and they would start talking you. Still, we have this big problem. No matter what you show to the surgeon, any given day, he or she will be about 70% sure about what he or she can see. So how we can bridge that, we haven't figured out. They have very difficult time to live in the operating room without a radiologist. How this will be solved, I don't know, because that's not a technical question. What I wanted to still show in the last 1 or 2 minutes is the iKnife device. So normally, the electrocautery smoke is a waste product that goes away. But what if you are Zoltan Takacs, as brilliant as he is, and he invented with Waters Corporation how to clean the smoke, how to accelerate the remaining ions, separate them, and from a big sniff of smoke, a couple of nanograms of ions can be put through a mass spectrometer, a time-of-flight mass spectrometer. And then so happens that the spectra can be characteristic to the tissue where it came from. You can tell apart horse from donkey, cats from cats, and all sorts of things. And of course, the big question whether you can make a subtle decision and characterize tissue from cats. And that's what my brilliant partner in crime of science, Parvin Musavi, comes in.
I think I can't hear Gabor anymore. So sorry, Gabor, you were just phasing out for a moment.
Oh, did I?
Yeah, so if you go back one slide, I think we've, and then resume from there maybe.
Right here?
One back, this one, yeah.
REIMS. Oh, maybe this was too much bandwidth. So you can hear it now?
Yeah, so I think we got to the end of that slide. Yeah.
Okay, so smoke, machine learning the smoke.
Yes.
So this go through this $500,000 machine that we got now 5 of them from voters, and Parvin is deep learning the spectrum of the smoke. Of course, it's lots of pesky histopathological footwork, because you have to be then incinerating a lot of pathological samples to have the data for reading. So if you are tracking what Parvin is putting out and TBME, IPCAI, MICAI, and everything, you will have a good idea. I don't have a page here to list all the good stuff that Parvin is now doing, and I'm honored and happy to be tagging along on that beautiful thing. So this is fine, but how we do interventions with this monster? Well, put a tracker on that. This is what we did. Put the tracker on the electrocautery, turn on the mass spec machine, and this is what we got. This is the tumor. This is the yellow is the trajectory where the tumor supposedly went in normal tissue, and the red when the machine was beeping cancer. Now this is totally nonsense, right? There's no such thing. This also cannot happen, because this is outside the patient. What can possibly happen here? Well, the pisser is that that machine has an unpredictable time delay between ½ second and 2 seconds, depending on how many bends you have on the flex pipe. You have this delay, and there is no telling what the delay will be. Oops. Also, the mass spectra changes with the electrocautery level. It changes whether I'm cutting, whether I'm coagulating, whether low energy, high energy, and whether when the energy is on. So the energy state is totally unknown, and the biggest, well, not surprised, because we knew that none of this electrocautery and any kind of surgical tool maker provides any kind of digital information out of the machine. We have no idea what these machines are doing. So we got to do something about that. So this is what it is now, the 4D navigated iKnife. So we actually put an USB oscilloscope on the power feed of the electrocautery. We machine learn first the scope signal to figure out what the cautery did, and then we oh, where is it? Then we, oops, I'm missing link here. So we jointly deep learn with the cautery, with the energy information and the spectrum. We deep learn now, re-deep learn the smoke, and out comes what we think is now correct. When we have a tumor, this is the electrocautery, and book, it caught a red. This seems to be a satellite lesion. We didn't think it was there. It was not in the original contour, but the surgeon caught it up as he went. Now there is a new plan, and to have a cavity shading on the bottom, so we don't have to bring this woman back for resurgery, and hopefully still save on the resection. So this is in clinical trials in skin cancer resection, breast cancer resection, tongue cancer is starting up. So this is very, very ongoing. But again, none of this would be remotely possible if the platform could not be registering all this ancillary data in space and time and replay it back for the surgeon to trace back the tool and trace back the smoke to where it was. So I'd like to finish with this one, and just the one takeaway message, that use, please, Slicer, MITK, Custus, I don't know what you use, but you do use something Don't go home and hack out your things. Don't reinvent in this, and concentrate your science, energy, inventions, patents, whatever else you want on the true science in the 0.01, and let us please worry about the rest for you, because that's our mandate, to boost, enable other people's work, in which I found immense satisfaction. Thank you.